Hello and welcome everyone to the first talk after the lunch break. I hope you all had a good lunch break, and if you're feeling a little bit full, then no problem, because now the rovers are going to do the movement. So we have a great talk with you by two people from WARR Space Robotics, which is a student group and a subsection of WARR, the scientific work group for Rocketry and Spaceflight. Our two speakers are, first of all, Gaia, who has a background in mechanical engineering and currently studies aerospace engineering. She's been responsible for the wheel suspension drive optimization of the last rover, and she's set the groundwork for the ERC MARI rover and contributed to the payload architecture. And then we have Brandon, who has been a member of WARR Space Robotics since 2018, both in the PR and the mechanical teams. He designed and manufactured the Warthog's rover's robotic arm. I hope I'm pronouncing that correctly, and also the last rover's chassis. Since August 21, he has overseen all technical and managerial activities with WARR Space Robotics. He's also responsible for the team's financial planning, and now the stage is yours.
All right.
One more thing. This talk is also live streamed on Zoom, so the people on Zoom, please feel free to ask questions via Zoom. Stage is yours.
Well, thank you very much for that heartfelt introduction, Christoph. But as you mentioned, we're the first talk after lunch, so as such, we designed a presentation to get you all out of the food coma that you're all probably in right now. I sure am in a bit of a food coma myself, right? So we have a surprise quiz round. So let's see. I want some full audience participation. If you know the answer, shout out the answer or raise your hand. We're just going to, yeah, exactly, like that, like that guy, gentleman in the row there. So question number one. What does VAR stand for?
It's a hard one.
It's a hard one. Who was paying attention to the, the introduction of Christoph? Anybody?
Eventually.
Actually, nope, there is no rover in the title. Right, so we are the scientific work group for Rocketry and Spaceflight. It's a German acronym, Wissenschaftliche Arbeitsgemeinschaft für Raketentechnik und Raumfahrt. Nothing to do with weapons or anything like that. We're a student team, but we'll get to that later. Question number two: name 3 of the TUM campus locations. Garching, yes, that's number 1. I heard München also, so that's a giveaway. So what's the third one? Huh? Freising, yeah, that's a very important one. Yeah, I always love the.
It was a tough one. Good.
Yeah. I'm surprised nobody mentioned the Ottobrunn campus that we don't talk about, because we're really sad that we have to go there. All right. Question number 3. What is the name of the ESA Mars rover project? I'll take either the name of the rover or the entire project itself. Nope. No.
We have a winner.
Who? What? Who said?
You.
Oh, ExoMars. Yeah, there we go. There you go. Yeah, it's the ExoMars project with the Rosalind Franklin rover. Right. Question number 4, it's getting a little bit more tricky. What is the name of the 3D printing method which uses a concentrated energy source to generate solid objects out of metal or polymer powder? The generalization, the general term for it? So SLS is not the normgerechte term for it. Instead, it's powder bed fusion, PBF. So SLS is a type of powder bed fusion, but yeah, that's going to be an important part of our talk later. We'll get there when we get there. Question number 5, an even more difficult question. What was the one big idea in space technology that we wanted everybody to remember from our last Big Tech Day presentation? It was back in 2021, so it's a bit of a long stretch, but anybody here saw that presentation? Hey, we got a few fans of ours, apparently. Any guesses?
It has to do with rovers.
Yes, exactly. Yep. So that one big idea was in situ resource utilization, ISRU. We're going to talk about that a little bit more also in the presentation. And final question, most important one. Who here is absolutely thrilled to be at the Big Tech Day 2024? Yeah, that's what I like to see. All right, the mandatory warm-up section is now done, so we can go on with our presentation. So first of all, who we are. We are part of a larger association called WARR, which was founded in 1962 to compensate for the university's lack of an aerospace space technology faculty. Currently, we have 5 of them, so we've grown significantly in the academic side of things. But even still, to this day, we're complementing that the academic education that our students get in the lecture with practical scientific research work. We've been a nonprofit organization within the TUM since 2015. We have currently over 400 active members, all students, and we are the largest R&D student organization for space technologies. There you can see all of our 4 projects right here, ranging from biological experiments in zero gravity, of course, rovers and a bunch of other space robotic equipment. Rocketry, I'm pretty sure that's quite self-explanatory. And MOVE, they do CubeSats. They actually have, what is it now, 1 or 2? No, they have 2 in orbit right now, yes. Okay, wonderful, but we're here to talk about WARR Space Robotics. So, as you probably guessed, we're primarily preoccupied with rovers. For those of you who don't know what a rover is, it's basically a space car. We have made so far 3 of them, 3 big ones. The first one was the Warthog, that was mentioned during the introduction. It was designed with the intention of participating at the European Rover Challenge in 2018 and 2019. After that, we decided to take a little bit more of a scientific approach, and we made the big one, the one from 2021, LARS, the Lunar Automated Rover for Solar Sintering. Unfortunately, we couldn't bring him again this year because logistical issues. But yeah, he is currently in storage. And our current rover is Marie. We can't bring her either because our team is currently in Garching doing some work on it, so we couldn't bring it to the event, unfortunately. But we would have loved to bring her and drive her around. Right. Our projects, the 2 big rover projects were Crater. So Crater corresponds to the Marie rover. You can also see a little Magus right over here making a cameo here because he's our autonomous driving test platform. So before we test our software on the big rover, we have a little toy that we can verify all the software on. And then, of course, Project Rebels, the older project, which focuses on ISRU lunar construction. So we essentially integrate a large rover with this manufacturing process, this PBF printing process, which uses concentrated sunlight to generate structures from sand. So you can see a solid line of sand here developing in the wake of that moving beam of light. In addition, we don't just do rovers. We have a space elevator team, and we have a vampire project that's working on a lightweight lunar exploration probe. It's essentially a rocket-powered drone. We're not going to talk about these 2 projects too much today, but if these pique your interest, we have a contact slide at the very end, and we'd love to geek out more with you about that in our own time. But today, we're going to focus mainly on rovers. So, because I kept on mentioning our previous talk, I want to have some kind of continuity and kind of bring everybody up to date on the updates since 2021, because there are quite a few of them. So yeah, a test campaign happened in 2023, and we just want to present our findings from there. Just very quickly, for those of you who didn't see the previous presentation, the goal is to enable a sustainable human presence on the lunar surface using these autonomous construction rovers. So the idea is to leverage ISRU. In situ resource utilization is basically using locally available resources in order to make your mission progress. A very tangible example of that is from the beloved film The Martian, where astronaut Watney used his own feces to terraform Martian regolith in order to make poop potatoes, which he used to survive for an extended period of time. So that is actually the crux of in situ resource utilization, using locally available fecal matter and regolith in order to generate usable resources, in this case, food. So how exactly are we leveraging ISRU? We are using it in the context of the Moon Village, the international collaboration between all the various space agencies to create this base where we can do research on the lunar surface. Whether it's creating streets, landing pads, or in this case, a radiation and micro-meteorite shield for the habitat itself, we need some kind of manufacturing process to solidify locally available regolith. And that is exactly what we're aiming for here. So the existing technologies takes this solar sintering PBF printer. So it's a large lens, concentrates sunlight to a small point, and we move the point around to harden parts of a powder bed. And we combine that with this standard space exploration rover, pedigree from NASA, ESA, Curiosity, Opportunity, ExoMars, all of those rovers, and we combine them to LARS, the Lunar Automated Rover Solar Sintering. You can see we greatly decreased the size of the printer, and we greatly widened the geometry of the rover to accommodate this payload. Right, so last time we presented some of the solid structures that we made in our 2021 field campaign. We primarily used this quartz sand and soda mixture because we didn't have access to regolith simulant, and it was infeasible for us because regolith simulant is a little bit temperamental to work with because it's such a fine powder, and every minor change in the temperature of your spot will lead to very different results. So we simplified and we created a proof of concept first. But we investigated these issues here, particularly the degree of freedom, because we needed some kind of autofocus mechanism in order to regulate the temperature of our spot. And we were eventually able to graduate to real regolith simulant. So it's still not real regolith because that's kind of logistically impossible to obtain large quantities of. But we were able to first, it was essentially a very informal parameter study. We were looking for the different printing speeds and energy that we needed to create a solid line of sintered material. First, we created a line of glass beads because our temperature was way too high. Not really useful if you have a bunch of balls when you want a solid wall. Then we got closer. We got a sort of agglutinate, it's called, where we created the top surface that was completely glass, but the lower surface is actually exactly what we're looking for, a sintered region. But then we fine-tuned the parameters even more, and we got finally a line right here. And then we took it a step further, and we said, why don't we try to do a second layer on top of that? And that's exactly what you can see here. One sintered layer, and because of some strange, let's say, hiccups with the focusing, we have a slightly agglutinate layer on top of it that's fused to the bottom one. Right, but that's it from Project Rebels. I'm going to now hand the word over to Gaia, and she's going to talk about Project Creator.
Thank you, Brendan. Yeah, so let's continue our journey through space. We just left the moon. We established our moon village by means of LARS, our Lunar Autonomous Rover. And now the next step would be Mars. I said the moon? Yeah, whatever.
We did with the moon, now we're in Mars.
Now we're Mars. Sorry. Now we're heading to Mars. So you may picture a year very far from now where there's going to be the first manned mission on Mars, and how can we achieve that? Project Creator aims to explore Mars, the surface of Mars, and enable colonization for humans to get there. So we would want to deliver a Mars rover to be able to assess and prepare the landing site for the first astronaut to get to the red planet, to conduct safety and environmental evaluation, to establish the initial communication system and support system, and to explore potential in situ resources. How does Marie do this? So Marie mission aims to classify and map the terrain of dedicated location on Mars. Our destination would be Noctis Labyrinth. We would like to investigate the resources and the possibility of finding water as an ancient glacier underneath the crater. We would explore with Marie functionality, construction techniques in order to enable the astronaut to already have a base when they eventually would land there. And we would do system checks for the rover as a self-sustained operation. So there will be very little to none human interaction to our rover Marie. This is our mission, but how do we accomplish this being on Earth? That's a big question, right? Because there's probably not going to be a flight to Mars anytime soon with our rover Marie. And that's why we detected a fairly advantaged analog environment. It's called Marsyard, and that's in Poland. And that's where one of the biggest European competition for rover takes place. So besides our mission, as a team, as a student team, our goal as research, we would love to use Marie as a test platform for any research institution that's trying to develop a planetary instrument for exploration. We would like to foster education for our students, so let them apply the knowledge that they gain during their studies, and showcase our expertise to a well-known competition. Now we look a little bit more into Marie itself. So Marie stands for Martian Autonomous Rover for Experimentation and Exploration. As you can see here, the drive system or the rover itself is equipped with independently steered compliant wheel mechanism and a double rocker suspension system with a differential gear linkage inside the body box. And the platform is supposed to do autonomous navigation and can be equipped with different payloads. In-house, we are developing currently 2 payloads, a 5 degrees of freedom robotic manipulator with modular and effector mechanism, and the second payload, which would enable us to do science on the terrain, on the Martian terrain, is shovel system storage mechanism, where we would collect the samples through our shovel and then store them, weight them, and analyze them on board in the storage system. How do we do this? So we come up with an idea, and believe me, we had plenty of insane ideas. We try to roughly prove it through quick prototyping. You can see here the very first wheel, crater wheel assembled, a Barilla box because we didn't have enough. We didn't have enough 3D printing for Magus, and then we designed this on CAD. So we fuse quick prototyping and fast access to workshop with simulations to validate our design and eventually take it to the final next step, which will be the real manufacturing. Manufacturing is mostly done in-house. Eventually, we also outsource. It's fun, exhausting time for the team. We spend endlessly time in makerspace, but at the end, the results gratifies the work. Once we have the hardware and it's realized, the last step to take is actually to make our rover alive. And that's where a lot of assembly, integration, and testing takes place. This is probably the most thrilling part of our project, because when you do your things, when you do prototyping and then you do simulation, you don't really have a feeling how this is going to look like at the end. And when you put it together and you see, at first usually never works, but then after a couple of trials, then it moves. For the development of electrical software, I would give it back to Brandon.
Yeah, a bit of a disclosure here. We kind of, because we're both from the mechanical side of development, we kind of rock, paper, scissors to decide who does the electrical and software part.
And I was lucky.
I lost. So for the questions afterwards, please play nicely with me. I could direct you to other members of our team who are more experts in software, particularly because I think that's going to be more interesting here. But I'll do my best to answer your questions. We'll just say that. So, a little bit about a day in the life of an electrical engineer on our project. So, most of our electrical engineers do PCB development, of course. The first step to that would be to create whatever circuit that they're trying to do. So, this current circuit is for an electronic speed controller, an ERC, with which we use to control 2 brushless DC motors at a time. First step, find your components, research, and make a circuit out of that. We use KiCad. It's an open source software, which is actually a lot more convenient for us to use than more heavy software like Eagle or similar. So once we have a circuit design, we gotta put all the components out onto an actual board. We do PCB layout, also using KiCad, and you can see here this very abstract circuit being placed concretely onto the form factor of an actual PCB board. Next step is to actually manufacture the board. We work with a bunch of different PCB manufacturers, namely JLC PCB and Eurocircuits. We send them CAM files, and they send us a PCB blank. What do we do with a PCB blank? Well, good question. We do some soldering and testing, because we need to put all the components that we decided, all those fresh, small, hard to find, easy to lose components, right onto the board. We do soldering, and of course, with a lot of soldering and testing, there's a lot of frying and crying as well, because electronics love to do that. There's a running joke amongst electrical engineers that every piece of hardware has magic smoke stored in it that actually makes it work. And in testing, what happens is the magic smoke escapes, and now it doesn't work anymore. So there's quite a lot of that. In our defense, we were trying to get the magic smoke to appear just to abuse test our electronics, but even still, it's a frustrating experience that is also accompanied by some alcoholism sometimes. But eventually, once you soldier through all of the difficulties, all of the smoke, it works in the end. And we had the honor of presenting our rover to Minister President Söder and Staatsminister Blume at a semester opening event at our university. Yeah, it all works out in the end. We did enough elbow grease, you know? Onto the software system. So the main objective of our software team is to enable the autonomous navigation of a Mars-like environment. So here you can see an aerial shot of the Mars yard from the European Rover Challenge. There's a lot of different craters and mountains and large rocks and very loose ground. And the rover has to decide which path to take through this entire gauntlet of different challenges. How do we do that? We have a bunch of sensors. A large sensor suite includes LiDARs, RGBD cameras, wheel encoders, and a GNSS module. And all of these sensors get fed into our perception algorithm. So we do a little bit of a SLAM localization and mapping, and also detection of a variety of different objects. Then we have a little loop here, which involves planning and control. So first of all of the processed raw data from the sensors gets fed to the planning algorithm, where we have a global planner that says, okay, we're trying to aim for a particular waypoint. We have the behavior planner, which is a state machine that gets the go-between between those two, and then the local planner says, okay, we have a particular goal in mind. How do we go about doing that? Once that's been decided, we go to the control, and the control tells all of our actuators what exactly they need to do in order to get to a particular point. So I keep on citing the example of a waypoint, because on the Mars yard we'd have AR tags scattered throughout the field, and we need to get as close as possible to these because they're a point of interest, a point of scientific interest. We use a lot of ROS, Robot Operating System, for the majority of our software. Lessons learned from the previous rover, which ran on a little real-time operating system called RODOS. It was meant to be a lot more robust for an actual space environment, but we learned we're a student team, we're mainly working with analog environments here on Earth, and we weren't able to actually properly leverage all of the benefits of the redundancy that is afforded by a real-time operating system like RODOS. So we said, okay, let's keep it simple, silly, go back to something that would actually work for us for our application, and that's why we decided to go back to ROS. Yeah, I actually did not notice that was right there, but yeah, keep it simple, stupid. That was the guiding wisdom for our entire software. Right, so I already briefly mentioned that, but the key challenge is to have accurate, complete, and robust perception. So we have our SLAM algorithms, we do sensor fusion. I was also promised that on this slide there'd be a very fun little meme of ours that we would love to circulate. It's our beloved SLAM cat. So it's just imagine a picture of a cat being fed a lot of spaghetti, and then all of the different sensor data was getting put into it. It's adorable, but it didn't make it into the presentation, unfortunately. But it's a really good analogy for what we're trying to achieve here. We take all this sensor data, we stuff it into our SLAM cat, and eventually we get the cat to control the rest of the rover. Right. So then we have a nice little simulation that we'd like to show you. I don't know how it'll work with the media change, because I opened a browser. So is it going to be automatically shown to zoom? Let's see. Oops. If you can't see this in Zoom, apologies. But here you can see a small little autonomy demo in Gazebo. So we have you can see the path planning in action. Forgot to mention the data set that we used to power the SLAM algorithm is an open source package from NASA called AI for Mars. And this sample terrain, I believe, is provided from the ERC. Yep, but it's just navigating to a particular point of interest here with an AR tag. Right. Then back to the presentation. Uh-oh, we lost our place. Right, and finally the cherry on top. In addition to all of that software, we also do some remote operations and telemetry, so we need to have some kind of ground station so that we have a user interface with the operator. So you can see some telemetry data from all the different hardware, and you can also send commands to the rover to do driving or to actuate its different payloads. Right, next step, so I focused mainly on the navigation aspect of the autonomy, but in the near future, we are also looking to automate the sampling and the maintenance/repair, so the automate the operation of our payloads on our rover right now. So we already mentioned the regolith sampling system and the robotic manipulator, but currently we have them purely user-controlled. The idea is in the future, because for an analog mission, we want the rover to be completely autonomous. Also these tasks, the sampling and the maintenance, to be done autonomously as well. Right, so then,
what comes after?
What comes after? So I think Gaia is going to take the first bit of this.
So what do we want to do? Our main goal after the first year of developing our marine rover is to participate of one of the world challenge available for rover teams. The nearest goal will be to participate at the ERC 2025, that's in India, and develop on top of it a self-organized test campaign at the DLR facility, as well as switching with Lars to the Lunar facility, and then eventually the ultimate goal for us will be to participate at the URC in the US and show our capabilities there, as well as the ERC, which is our main target in the European Rover Challenge.
Yes, and now the absolute last words from the presentation. Breaking stuff is good, really. It's the only way that we actually learn to grow as a student team. It's only through the failures that you're actually able to you prove your worth. You know, so at these analog test facilities, we expect certain issues. For instance, regolith has a terrible habit of chewing through every single mechanical component, exposed and unexposed. You can see here the wheels from the NASA's Curiosity rover, and just the abuse that this really abrasive material can do. We have to mitigate it somehow. In addition to that, we expect some suboptimal driving kinematics due to gravity offloading. So normally we're testing it under Earth gravitational conditions. We usually have some kind of offloading mechanism, like a crane, to lift the rover up so that it simulates, for instance, a sixth of the gravity like on the moon. And that completely changes the driving dynamics. And that's something that we're also considering. And finally, low lighting or intermittent lighting conditions, which would be existent if we have a solar array, changing how illuminated the Mars or lunar yard is. So we're preparing for these issues. These are our so-called known unknowns. Yeah. So we have design controls to protect our rover against this. There's a saying that testing will reveal our shortcomings, so our unknown unknowns. That's those are the things that really make or break a project. So how you deal with the unknown unknowns, i.e. via testing, will decide the success or failure of your project. So our motto is break stuff now to develop the technology before it actually matters in a competition or in a real mission. So before we go on to questions, we'd like to do a special thank you to our supporters. Of course, TNG, you were very helpful to us in order to achieve our project goals. But yes, we would like to do a thank you to everyone who has helped us over the course of our...
Participated.
Yep. So, without further ado, I think we could move on to questions.
Yeah, so let's thank our speakers, Gaia and Brandon. So before I break something and maybe break poor little Magus, let's dive right into questions. Please, if you're on Zoom, just type it in the chat. If you're back there, I will come to you with a mic.
If it's possible to switch back to the other presentation, we do have a slide after that for anyone who wants to keep in contact with us.
Okay, I have 3 questions.
Sure.
First question, on Earth we have a magnet field and so certain protection against radiation and solar particles. How do you want to do that for the Mars thing? Second question is the speed of the simulation, the rover, what speed was that? Was it a live picture when you showed us this thing? How many meters per second was that running? And what was the third? Okay, later.
Okay, I'll address those questions in reverse. So unfortunately, I don't know the speed of that simulation. I just know the speed of the actual rover. The rover is capped at 0.5 meters per second. That's its top velocity. But under normal operations, I think we go closer to 0.3, right?
Yeah.
Yeah, 0.3.
Up to 0.3.
Up to 0.3 meters per second, yes. And then the first question, to be fairly honest, the radiation is not one of the problems that we're investigating right now, because as we mentioned, we're on an analog mission, and the analog mission is getting the technology developed first under Earth conditions. So to address the radiation, there are a lot of ready-made electronic solutions from a variety of different manufacturers that sort of alleviate that problem for us, but of course there are some design aspects that need to supplement those ready-made solutions, but we're not investigating them at the moment.
Okay, so the third question, sorry. You have a sensor for global satellite navigation, which won't exist on Mars, probably?
Yes.
So that's the same thing, we are just doing that for the Earth environment now?
So the original software architecture actually did not include the GNSS.
Yeah.
It was only due to a rule change at our competition that they said, okay, we're going way far into the future and we're assuming already that there's a satellite constellation around Mars already existing. And that was the motivation. But still, it didn't really sit right with us to use GPS for a Mars rover. You're completely right. But yeah, it was just a matter of the competition.
Yeah, thanks too. Next question.
So first, thank you for the wonderful talk. And my first question about these Mars test site. How sure are we that this is a compatible test site, that these are Mars environments or something like that?
You want to take it?
I can take it.
Okay. Right.
Yeah, so if you're referring to the analog Mars yard, that's basically the organizers are scientists and aerospace engineers that are giving this opportunity to student teams to resemble the Mars conditions on such the meaning of the terrain. So no atmospheric conditions will be simulated. It's just the composition of the terrain and slopes, eventually climbing and declimbing, and roughness of the terrain. It's going to be mostly the soil resembling Mars.
Okay, but the soil is resembling Mars.
It's resembling Mars, yes.
So from the small regolith samples that we have collected from actual lunar and Mars missions, we were able to reverse engineer. Okay, this is the chemical composition of these of the soil sample, and this is the physical abrasive, really fine dust-like capabilities of it. So they focused mainly on those two aspects, and
for us to drive to.
That's the most important things for us also.
Yeah.
Yep.
Okay, next question.
Yes, thank you for the talk. It was rather interesting, very interesting. I have a question. So there is a delay in communication with Mars, of course, between 4 and 24 minutes usually. Did you take that into account when you did like hands-on control of the rover, or is it for a future experiment, for example?
So the primary mitigation that we're using against this latency in the communication is actually the autonomous operation. So under an actual mission, we're going to try to automate as much of the operations as we can and only send back critical telemetry, video feed every now and then for the remote operator. But in 2021, at our field campaign in Igluna, we did have a sort of artificial delay for communicating with the rover. So it was mostly to approximate the moon delay. As of now, we don't consider it yet either, because it's
the rover should be fully autonomous.
Yes, we focus mainly on getting the autonomy.
The least interference from Earth. That is the mission.
Okay, speaking of communications, next question. Yep, you have to endure a little latency until I get there.
Thank you. So you showed one of your earlier rovers which had a wide wheelbase, 6 wheels, big wheels, and this newest one had only 4 and smaller ones. It was also taller.
Yeah.
What made you decide to have a less stable configuration?
I can take that. Yeah, so first of all, lesson learned. The previous rover was too heavy, and it was not meant to drive too far. Instead, it was meant to be built to enable sintering while being stable. This rover here, its intention is to actually navigate the terrain of Mars, so we need to ensure light weight, overcoming obstacles, and easy mobility. So from our lesson learned of the previous rover, we realized that too heavy was not good. We could have reduced the design complexity by going with 4 wheels, and the differential linkage ensures stable operation when you try to navigate uneasy terrain.
Also, you have to consider that this rover right here is much smaller than the other rover. So the main reason why we had to widen the rover was because to accommodate the payload that was moving out in front of it.
Yeah, these current payloads are way stationary and way smaller.
Yep.
The arm is meant to do operation, and the shovel is meant to do science.
Okay.
Okay, so you're talking about, for example, the Lunar rover for solar sintering. How large are the structures this rover can create? Like you were talking about radiation shielding, but like those are multi-ton structures.
Yeah, the scalability question is a very it's a very open question for us. So there were very early on in the phase 0 of our project, we come up with a bunch of different operational modes. For instance, having the rover drive on a structure that it's currently printing in order to create subsequent layers. So currently, for Lars, the printing area is capped at around 20 centimeters by 20 centimeters, if I remember correctly. We haven't really considered yet how it's going to be scaled. So there are alternate solutions, for instance, using a microwave to greatly harden a large amount of area at a given time, as opposed to just having one single point like in regular PBF. But we started with the PBF, the solar sintering, because it's much more accessible for a student team as opposed to like having to go through all the safety hoops for microwaves, for instance. In addition, I lost my train of thought there. There was.
If I can add,
Sure.
Lars is supposed to be a proof of concept. So our vision doesn't necessarily resemble what we accomplish with the hardware. So our target was to prove that you can sinter in this way using the rover. Once that was achieved, the team also had other needs, such as developing autonomous driving. So that's why we stopped there. We didn't really.
You didn't tell us about your power pack. How much battery do you have? What's the operational range?
So we've actually never been able to completely deplete our battery. We haven't done that much abusive of testing. We do have I don't know off the top of it. We have a lithium iron phosphate battery, 48 volts. I don't know the amount of time that it takes to completely deplete it. I know for a fact it lasts at least 90 minutes. But as for recharging, we don't have any solar panels or anything
No.
to do in-place charging, because that's also not what our focus was. We focused mainly on these particular payload, the payload development, and the autonomous driving. It is possible to integrate just a solar cell to do some in-place charging, but it wasn't a priority for us.
Yeah.
Okay, one question in the front.
Yeah, thanks. Maybe to connect to the battery question, so if it was like a real Mars mission, or also for the rovers that are there now, are solar cells like photovoltaic effective on Mars and potentially also further planets, or would nuclear also be an option like with the Voyager probes or so?
Yeah, so I would say both. There is no reason why nuclear wouldn't do the job. I think at the moment our resources or internal resources will be more towards solar panels. And as Brendan already mentioned, we didn't really investigate that domain yet, because any analog mission we're doing on Earth is sufficient to have a battery on board. So we did not pursue that path yet.
Although it is one of the it's one of the predominant concepts for having a more sustainable power source on board a hypothetical lunar base. Which is why a lot of other similar researchers who do much in the way of lunar construction, they're opting more for the laser aspect, because they're already assuming that there's going to be a nuclear power plant on the moon. Because that seems to be the tendency of the researchers. Yeah, and of course we didn't do lasers primarily because of the learning curve for students, but also we thought it's a much more elegant solution, a more pure expression of ISRU if you're using only the sunlight and the regolith, as opposed to depending on nuclear power to run a compressor and cool your laser and power the laser and yeah, whatnot.
I understood your mission is going to take place in like 2055 or something like that, and all you do at the moment is research. How do you make sure that like the outcome, the object itself, the documentation is someone can find it or remember it when it's really needed?
Yeah, so ideally, this is in the future, this is after Starship could make the launch, and eventually we can actually go to the moon and make a base and then travel to Mars. So this is the vision is for us a way to develop technologies. The rest, what we're trying to do is to prove that you can have a full autonomous rover doing different tasks without the need of human operator interacting with it. So we want to prove that you can have a platform running autonomously and being able to self-fix eventual damages and foster the possibility of human landing on Mars, such that science collection, so figuring out if you can use the resources there. We're documenting everything, and if there's going to be a ride, we're going to take it with Marie.
Yep, to directly answer the question though, in one word, GitLab.
Yeah, that's where we store our documentation.
Yep.
Okay, maybe one more question from me. So you brought little Magus here. I also saw big Magus on the slides, or I think you called him Minister President Söder.
Yeah.
Did the two ever meet and
Yes,
did they get along well?
Actually, yes. A funny story about that. Our chairman of the WARR was presenting him to Big Magus for just for the sake of no confusion, and he didn't trust himself to introduce Minister President Söder to his small little doppelganger. So he just called it, so he was asked, does it have a name? He said, a rover.
Okay, no more questions, I guess. Then let's thank our speakers once again.
Thank you very much.